Thank you for joining today's webinar, Vault-Free, Cobalt-Free Radiosurgery, Technology Review and Clinical Experience at the Swiss Neuro Radiosurgery Center. The RSS would like to thank our ZAP Surgical Systems for supporting this webinar through an unrestricted educational grant. It's my pleasure to introduce you to our moderator, Dr. Pantaleo Romanelli. Dr. Romanelli is the Scientific Director for Brain Radiosurgery at the Centro Diagnostico Italiano in Milan, Italy. He is also Chief Medical Officer at AB Medica and is a leading scientist of the neuroscience research projects at the European Synchrotron Research Facility in Grenoble, France. He received his medical degree summa cum laude at the Seccone University of Naples, Italy, and completed fellowship training in epilepsy surgery, functional neurosurgery, and stereotactic radiosurgery at the New York Medical College, New York University, and at Stanford University. He is currently professor of the biomedical technologies by the Italian National Authority. He has subscribed 4 patents on wireless brain signal transmission using medical devices. He's authored more than 70 publications and was awarded the Pioneer of Medicine Award from the Society of Brain Mapping and Therapeutics. Welcome, Dr. Romanelli.
Thank you, Jan. So it's my pleasure to introduce Dr. Mack for this webinar. I just need to do a small correction because I'm not with AB Medica anymore for the last couple of years. So perhaps I sent a CV that needs to be updated. All the rest is correct. So I will proceed to introduce Dr. Mack. Dr. Mack got his PhD in physics at the University of Tübingen. He has been CEO at radiosurgical centers in Swiss for a long time, with a long experience, starting from the early 2000s. And after running a cyberknife center for several years, he's now implanting, he just implanted the new cobalt-free, volt-free ZAP system. So please, Dr. Mack, we would be so interested to hear your experience with this ZAP installation in Switzerland. So please go ahead.
Thank you very much for this kind introduction. It's a pleasure for me to be here. I hope all of you understand me well.
Yes, we hear you well. We do.
I'd like to lead you through the presentation by using following topics. I would like to remind us all on the basics of radiosurgery. And then I want to continue with dedicated devices for intracranial radiosurgery, focus on the technology concerning ZAP, then continue with the treatment procedure, then focus on some indications, followed by some QA measures, what we need concerning dedicated constructional requirements, and then try to find a summary. I think we all know basics of radiosurgery, and I don't want to go through all the points, but I think Lars Lexell was one of the main pioneers, and I know from his son, from Danny, that the motivation back in the 1950s to develop a dedicated radiosurgical device was given since the risk for mortality was up to 40% at that time at Karolinska. So he defined the need for radiosurgical device by saying the delivery of a single high dose of radiation to a small and critically located intracranial volume through the intact skull. So if we just look back what happened in the last century, there has been a lot of development going on. So the first stereotactic frames in neurosurgery were already developed in 1908, followed by stereotactic neurosurgery in humans by Spiegel, Weikes, and Lexell. In the 1940s, then the first experiments from Lexell with an X-ray tube. 1950s, then some developments in Berkeley with protons and helium ions. Then again, Larsen and Lexell with the prototype using protons in 1954. Then Kjellberg and Köhler in Harvard using protons for radiosurgery. Again, Lexell and Larsen with the gamma knife prototype in the 1960s. Then the first U model at the Karolinska in 1975. The first approaches with the linac by Betty and Darren Shinsky in 1982. Then an interesting concept by Bouvard in Gainesville by decoupling the linac by the use of a floor stand, which made it available to gain high accuracies concerning the isocenter. And then the further developments of gamma knife versions. And then in the end of the 19th, the idea of John Adler, who has had an education at the Karolinska, where he found that it was necessary to have a machine using the principles of radiosurgery for the complete body. So he developed the first robot-supported radiosurgery. Then further versions of the gamma knife, then the first idea of using a rotating linac with a tomotherapy, then different versions of the cyber knife from 2010 up to now. And then again, John Adler with the first gyroscopical radiosurgery ZAP-X device, about which I would like to give you a talk today. Another nice approach which I want to mention is, I was in Japan and I was surprised on the many dedicated devices concerning gamma knife and cyber knife in Japan, and they also use an approach called Bohr neutron capture therapy. So the idea is to selectively enrich the tumor cells with Bohr-10, then irradiate this cells with slow thermic neutrons, and by doing this, splitting the Bohr-10 nucleus into an alpha particle and into a lithium ion. And the nice thing about this chain reaction is that the range of the reaction products is approximately within the cell dimensions. So you gain a very high LET and thus a high RBV, and that means you need less dose. So it's a binary therapeutic concept, because the first part is an enrichment by and with Bohr-10, and then a irradiation with neutrons. So putting all together, this is the basic idea on radiosurgery. So the principle of fractionation, the classical division of the dose into many sessions, due to the fact that different tissues react differently sensitive to radiation, is replaced by portioning the dose into many geometric contributions. Radiosurgery is mostly given in one fraction, so the portioning of the dose into many geometric individual beams is the difference. We want to have or achieve extremely steep dose fall-offs at the edge. So we have gain a high dose and a high BD, and thus a high tumor control. Limitations are if the volume is too large, we have toxicity, we have malignant processes. According to LQ model, radiosurgery is maybe not the perfect idea, and strongly differing alpha and beta values for tumor and surrounding tissue are also maybe a challenge. So if we look at these graphs, which are all familiar to us, the idea would be have the chance to give enough dose in one session to gain a high tumor control on the one side, not causing side effects on the other. That means we have a certain therapeutic window which we can use. And we all know this graph at the down left side, we want to achieve a dose distribution coming from the outside with very low dose until the tumor starts, and have a steep dose rising to the tumor, and at the end of the tumor, steep dose fall off again. And the measure of quality is dependent on the device, technique, and dose planning. We want to achieve a maximum conformity and a maximum dose gradient. The goal is to reduce the dose to half within roughly 2 to 3 millimeters. And how can we achieve these high dose gradients? The main factor responsible for this is the penumbra. It's simply a geometric problem. If you look at the source size, you look at the distance from the source to the lesion, it is clear that if the distance is rather big, you develop a high shadow, which you don't want to have. That means what has an influence is the source to surface distance, the distance from the collimating systems to the target, the source size, and the quality of collimation, leakage, degree of focusing, etc. And if you look on the main representatives who deal with radiosurgery, if you look at the conventional linac, you have a focal spot about 1.3 millimeter, a rather high distance from the source to the lesion, and from the collimating system to the lesion. And if you look at the CyberKnife, it's a little bit smaller. If you look at the Gamma knife, you have already a strongly reduced SAD and a collimator to axis distance, and with the ZAP, it's roughly the same. That's the reason why I put the boundary. So these are the dedicated radiosurgical intracranial surgery systems, and these are the more universal systems. We all know from the daily routine that we always have to add a certain diagnostic uncertainty to the tumor, and if the tumor is moving, and further safety seem concerning to movement. We all have the feeling that nothing is moving in the brain, but if you look at this video, I just want to turn on. It's not working. Okay, I continue. So radiation physics plays an interesting role. We only can use 5% of the energy, because only 5% we can use to ionize the atoms. 95% of all the energy is converted into heat and vibration, so we cannot use this. Together with formation of highly reactive free radicals in chemistry, and concerning the direct breaking of molecular bonds, single or double strand breaks, we can achieve a destruction of the tumor. All effects leading to an overall biological effect. So what are the optimization criteria? We all know that we need to gain a high conformity index, or a conformity index. That means down here we have the perfect match, and up here it's too much, and there we have mismatches, so I think that is clear. But the second, which comes or plays a dominant role, is the gradient index. That means is how close can we squeeze the dose mesh to the tumor. Now, looking at the dedicated devices for intracranial radiosurgery, on the left-hand side you see the Gamma knife with the 192 sources arranged around the unit center point, all emitting rays at the same time. And in the middle you see the gyroscopic suspension of the linac at the ZAP. That means the geometry is rather similar. You have a main axis along in parallel to the couch, and then you have a oblique axis tilted by 45 degrees, and both axes have shells which are moving inside each other, and within the inner shell the linac and the X-ray system is mounted. So if you look at the spectrum which is used, again there's a similarity between the Gamma knife and the ZAP, because the Gamma knife is using cobalt-60, emitting with the same intensity at 117 and 133 MeV, delivering roughly 1.25 MeV. And if you look at the 3 MV linac with a maximum energy of 3 MV. It will have the strongest incident at roughly 1/3 of this maximum energy, delivering a spectrum of roughly 1 MeV, which is not that far away. So again, concerning the beam quality, we have a similarity. We also have a multi-isocentric approach. That means the lesion will be kind of covered by so-called isocenters or by spheres. And that means that the target is kind of pushed or pulled through the intrinsic focus of the machine. So every so-called shot or sphere is put together of a variety of beams, every single beam delivering only a small part of energy, but where in the area where all the beams intersect, we have enough reaction to cause effects which we would like to have. And so you can optimize concerning the collimation, the exposure time, the weighting of the shots, and concerning the overall treatment time. The tracking methods are in analogy to the cyberknife, so you can track according to a skull-based algorithm, which takes into account the radii of the curvatures of the bones, and the adjustments are made according to the DRRs which you have reconstructed due to the primary taken CT. You can correct for the translations and two rotations. So this is the machine, and it's in a side view. So this would be the axial gantry, to which everything is mounted. You see the gimbaled oblique gantry with the linac down here. This is the shielded treatment sphere weighing 28 tons. The patient is lying on a couch. With the imaging detector and the KV tube to control for the positioning of the patient, and then compare to the data by the primary taken CT. We have the collimator with a linac and the collimator wheel up here. The shielded rotary shell, which closes everything as soon as the patient is inside the machine. You have a detector for dose monitoring. So here you have the collimator with the wheel, and you have the different diameters between 4 and 25 millimeters, and there's one situation where you have a plug. That means you can block the beam. The drills are conically drilled. That means you have very, very little scatter within the collimator wheel. So this is a simplified geometrical representation. And that means since the linac is mounted in the inner shell, and the inner shell again is kind of moving around the basic axis, you have 1,800 positions multiplied by 9 collimator positions, and that leads more than 16,000 combinations which you can use. So this would be the situation. You have certain node positions which will be addressed by the linac during the therapy, and the target will be moved through the given intrinsic focus unit center point of the dedicated system. And after you have kind of treated one isocenter, the couch is going to move to the next part of the lesion, and then you start all over delivering the dose to this part of the lesion. This is the chance to verify the calculated dose in real time with MV imaging, and it gives you a feeling on how big are the deviations between the pre-calculated dose and what you actually allocated. So I hope. I don't know why it's not working. Just tested it, but it's not working.
You could try to hit play one more time.
I'm sorry. This is strange. May I continue? So the treatment procedure begins with imaging. So we have to make a mask. The mesh is heated up and pulled in a soft state over the head to the table and fixed in place. We'll have a CT with the mask, and we'll have an MRI without the mask because we can't squeeze the patient with the mask into the head coil. But the MRI scans will be co-registered with the CT with the mask. So this would be the situation in the planning system. So you have the CT with the MRI, and then the planning process would continue. So in this case, we'd have an acoustic neuroma, and this would be the multi-isocentric approach. So you semi-automatically place the shots, and then you get these isodose lines. Now, on the right-hand side, you see a mesh representation of the spheres, and this is a simplified representation of the beams matching in these points. So as soon as the dose planning is finished, the patient will be fixed, mounted with the mask to the table, lying on a headrest, be moved in this unit center point, and then the shell would close. There would be an X-ray, couple of images. These would be compared to the reconstructions taken before from the CT, and if the patient is in the right position, the application of dose can continue. And the follow-up ideally would be performed at the same scanner, the same sequences to perform exact volumetry. So concerning indications, it's mainly the same indications as with all the other radiosurgical devices. We have benign brain tumors, vestibular schwannoma, meningoma, pituitary, urinoma, glomeruloscular tumors, then malignant brain tumors, the metastasis, glioblastoma in a situation of recurrence, chondrosarcoma, chordoma, eye tumors would be the uveal melanoma, and malformations, mainly the AVMs, and functional trigeminal. So if we start with the vestibularis schwannoma, and this is planning which we performed many years ago at another device, we would like to gain steeper dose gradients to the cochlea. That would be ideal. Second, we would like to have very steep dose gradient to the facial nerve in front here. We would like to avoid symptoms, paresis or salivation, and we would like to achieve maybe some cold spots along this profile, because we have the feeling if we can manage to allow the nerve have some colds or some reliefs along its way through this channel, there would be a chance for a long hearing preservation. That is our feeling. And we observe, depending on this high dose rate, maybe the temporary swelling phenomenon can appear a little bit earlier than compared with a machine with a smaller dose rate. So this would be a vestibular schwannoma planned with a ZAP. It's very, very close and narrow following isodose lines. We have an example of a pituitary. Mostly we have the neurosurgeons take out part of the tumor before, and they leave a residual amount for us for intracranial radiosurgery. This is something we would want to address now in a study, that we, instead of irradiating the tumor bed after resection, we would like to have a pre-resection radiosurgery. Means that we perform radiosurgery of the solid tumor and afterwards open surgery, and then we have no cell entrainment by surgery, and we hope that we can achieve good clinical results. We have found out that approximately 14% of all the patients can gain a long-term survival, 5 to 7 years, if they undergo regularly follow-up, and we can continue with several radiosurgical treatments and with almost no cognitive deficits. That would be a metastasis with the ZAP, with all the narrow and close isodose lines again. This is the glioblastoma, where we would like to, but that's too early for us, would like to follow the approach by Christopher, who tried to, after open surgery and after classical radiotherapy of the tumor, but tried to form radiosurgery along the propagation directions defined in FLAIR, and he reached excellent results, being superior to the classical STUP scheme. So that is very, very interesting, and we try to learn how this can be performed. I think that could be a very interesting perspective for these patients. Uveal melanoma is an interesting case. This is a case which we have performed at a Gamma Knife for many, many years, and we now want to achieve this with this masque system, this fixation system, and we have a, by Oraya size, a lens system, a suction cap, which is put directly on the eye lens, and you can evacuate this by a small pump. So you would need no retroverbal anesthesia, you need no frame, and you need no tantalum clips, which you need if you send the patients to the proton. So we're very, very curious how this will work out. AVMs, as you know, it's mostly a challenging thing in defining correctly the nidus, and it's a very complicated situation. The higher the dose, the higher the optic duration, the higher the dose, the higher the induced side effects, the higher the dose, the less risk of bleeding and the bleeding function of age. So it's a complicated back and forth, and there are several concepts of staging if the volumes are too big concerning dose and volume. And you have to do something, because if you do nothing, the bleeding risk untreated is somewhere between 2 and 4% per year. Trigeminal, we have up to now 7 cases, out of which 6 give us a feedback that they have strong pain relief, which is a good sign. We always have situation between medications, Janetta surgery, thermocoagulation, and radiosurgery, and we follow the same approach as probably most of the centers that we would like to give. Between 1885 gray, close to the brainstem, because we also feel that in this region there is probably the best situation concerning the to gain a pain relief. The concept of treating along the trigeminal nerve is rarely practiced because it does not deliver better results. And the idea is that we would like to damage the axon, because then it cannot perform its function anymore, and would like to have some kind of a partial necrosis, and those effects would have an impact on the physiology and lead to 80% pain relief, by at the same time probably a percentage of 7% of numbness, and would probably, according to literature, need repeated therapy in 20 to 23%. And these would be an example of a dose planning for trigeminal. Please note that the red line is only the 4 gray line, And since the brainstem can accept something between 10, 12, 14 gray, we are in a very, very comfortable situation here. Concerning QA, I think we all have to face the problem that we need to take into account all these limbs: mechanical accuracy, the positioning of the patient, the biology, dose calculation, target definition, locking, and the imaging. I think imaging is very, very important, and we try to keep the overall accuracy somewhere shortly below 1 millimeter. And we have several phantoms to achieve this. Concerning the images, we have several positions in phantoms where we exactly know the geometric coordinates, try to find that out in a planning system, and we, in a wrong color representation, we get the feeling where the rods are not exactly represented, and then we go to the application manager, which will help us to tune the sequences. We have some special phantom head phantoms. We have some test inserts where we can insert film, and you see in this case the small artificial lesion, 8 times 4 times 4 millimeter, the exact dose distribution you could find on the film with an absolute dose measurement, that you not only hit the target exactly, but you can also verify the dose which you gave. And this would be for an acoustic neuroma if you have a film sandwich, you can really try to verify the dose distribution. Something concerning constructional requirements, you need rather high and a big room to bear the machine, and you need additional space beneath the ground, and you need static building measures to carry these 28 tons. So you need a pit below the ground. You do not need special radiation protection due to the self-shielding construction of the machine. So this is a situation in our building, and here you see there's a lid in the ceiling, so we could lift the machine from the top into the bunker. So this is a cut. You see the pit with the machine. In the ceiling, you see where the lid was opened, bringing the machine. Dimensions for the room are roughly 10 meters times 7 times 3 in height, and 28 tons weight on the pit. You need air conditioning, cooling to cool the linac. So, trying to find a summary, I think the importance of radiosurgery has changed. The method has gained importance. The classical principle of temporal proportioning the dose into different sensitivity of tissue of radiation is being replaced by geometric portioning of the dose into many individual beams. I think higher resolution imaging is absolutely essential. The better the imaging, the lower necessary margins. The overall accuracy of the system plays the overriding role. The scientific data in radiosurgery is documented in many ways. There are so many millions of patients treated with the gamma knife and more than 300,000 with the cyber knife. There are a vast mass of papers which document that the efficiency of this method. Summing up the factors which faces ZAP-X technology, it's a convincing concept by using elements of gamma knife and cyber knife. It's very precise, it's dedicated for intracranial radiosurgery. It's already mature concerning the hardware, which was developed by ZAP and partially with Varian. It's a multi-isocentric radiation principle, high dose gradients to a low penumbra, and thus delivering a very low out of field dose, uses magnetic drives, complex flange technologies. The first results at our center from approximately 7 patients are promising, although no long-term results are still available. You have to take into account you need enough space for bearing the machine and technical equipment, 10 by 7 by 3 meters. You need enough space for the pit beneath the ground level. So it's 5 times almost 3 times 1.5 meter in addition. And you need to make sure that it can carry 28 tons. No extra shielding in the sense of a classical bunker, since the machine is self-shielding. And you need no safeguarding measures, since there's no cobalt-60 used. Now there's one tracking algorithm, skull-based, available, and the sphere packing has to be performed mainly manually for the moment being. I think a main argument for us to go here is that complete center is integrated into a neuroscience institute. Constellation is unique because all necessary disciplines are under one roof. We have neurology, neurosurgery, neuroradiology, radiology, and physics. And scientifically, we are linked to the neurosurgical faculty of the University Hospital Basel, and we're supported by Hills-London, Endomine, Center for Microsurgery, and the Trimley Eye Clinic. And I want to especially say thank you to our fantastic team. We would have had no chance if they would not have helped us to bring this up. So I really feel honored to be part of them. So thank you very much for your attention, and I'm now open for questions.
Well, thank you, thank you, Dr. Mack. So we can start with questions. I have a question from Mr. Narendra Singh. He's asking if it's possible to integrate the system with MRI.
Whether you can embed MRI?
He's probably asking if it's possible to use MRI for the treatment planning. Well, I know already that you can, correct?
Oh, I mean, for the dose planning itself, CT is mandatory due to the fact that we use electron densities derived from the Hounsville unit. But we use the MRI for the anatomical definition of all the structures.
Yes, that's right. So, well, I have two questions myself. So, what about, what's your experience comparing this system with previous systems you have used, about the actual treatment time, so during delivery, and treatment planning time, so the time needed for the treatment planning itself? So what's your impression comparing this system with other systems? Is it faster, easier? What was your impression?
Well, to the first part of your question, the effective treatment time is composed of an effective beam on time and a time which you need for the setup of the patient and for the travel of the linac within the sphere. So the overall time for the first, I mean, when the patient comes in until he leaves is roughly between 30 and 45 minutes. The effective beam on time is only between 15 and 20 minutes, and the rest is just to position the patient and to allow the linac to address the next node position. So that is roughly the time consumption concerning treatment. Concerning the planning time, it depends on how many loops you want to take. For every loop, it takes you roughly, I don't know, maybe 20 minutes. And then you show the result to the neurosurgeons, radiation oncologist, and he says, okay, maybe you can do a little bit better concerning the constraints, a little bit better to the facial nerve, and you go again. So for every loop, you need maybe 20 minutes. So altogether, if you have two to three tries to really optimize and to end up with a sophisticated dose plan, it accumulates to, let's say, 1 hour per plan.
Well, that's not bad, actually. And Do you see advantages in using the 3 MV linac versus the 6 MV linac?
Well, I think they used on purpose linac with a lower energy because they wanted to be close to cobalt, because if you have the same beam arrangement and roughly the same beam quality, the results are probably very, very close to the gamma knife. I think that is the idea. And since you do not need a strong penetration in the brain, 3 MV is totally enough.
Yes, I agree with you. Okay, I don't see any other questions. So, Joanne, would you like to proceed with the video eventually?
Yes, I'm going to try and pull up the video for you. Let me just do that now.
Oh, you see all the video?
Can you see it?
Yes, I see it.
Great.
Yes, I see it also.
Okay, now you see the 45 centimeters from the source to the target. Now this is a collimator wheel with the different openings, collimator sizes. And now you will have the first X-ray fan in blue from different positions, and this will be compared to the DRRs, and then you will have an overlay, and the patient position will be corrected for. And now you see the degrees of freedom concerning the couch. So the couch will move the patient, and thus the target, which will be moved through the unit center points. Now this is the main axis, and now you see the oblique axis, and during treatment both axes will spin at the same time. Now you see the different node positions from which the linac can direct to the unit center point, and the lesion is pulled through the unit center point. So now you see some exemplary beams, and I think you now understand the principle. So now all beams are directed at one isocenter, and then the patient will be moved to a different position, and then you continue all over. So this is the exit dose, which will be compared to the pre-calculated dose. Perfect. Thank you very much.
Okay, thank you, Dr. Mack. So I don't see other questions at the moment. So thank you for the very interesting presentation. And well, we hope to hear more in the future. Thank you again.
Thank you.
Thank you, Drs. Romanelli and Mack, for taking time to support our educational mission. We hope you appreciate these webinars and will consider supporting the RSS by becoming a member.